Olá a todos, essa é a gravação do primeiro webinar do Simpósio de Engenharia Ferroviária, promovido pela Universidade Estadual de Campinas, Universidade de São Paulo, Universidade Federal do Espírito Santo, Universidade Federal de Juiz de Fora, Universidade Santa Cecília e Instituto Federal de São Paulo. Em nome da comissão organizadora, agradeço aos parceiros e apoiadores, a Vale, a MRS, a Greenbrier Maxon, a Amstead Rail, e a Bifer e a NTF pela divulgação. Nesse primeiro webinar, teremos o professor Roger Lewis, que é titular no Departamento de Engenharia Mecânica da Universidade de Sheffield. Ele trabalha há muitos anos com fenômenos ligados ao contato Roda-Trilho, em especial com aplicações na área ferroviária. Seu currículo resumido está na página do simpósio. A apresentação será em inglês e versará sobre a interface Roda-Trilho, medição, entendimento e solução de problemas. As legendas foram geradas automaticamente.
Okay, thank you very much for the invitation to speak. It's a great honour to be joining you today, and thank you very much for the introduction. I've been working in tribology for quite a long time now, 20 years. Through all of that time, I've been working on wheel-rail interface issues, and today I'm going to give you a snapshot of some of the bits of research that we've been doing. So a brief overview of what I'm going to talk about. I'll give you a little introduction to the University of Sheffield. And then I'm going to go through perhaps a broader picture of some of the research we do here on railway engineering, most of which is on the wheel-rail interface. And then I'm going to go through some case studies on work we've done or are doing on wheel-rail interface issues based around measurements of the wheel-rail interface, understanding and overcoming wear problems. And then a bit at the end about modelling of friction in the wheel-rail interface, here specifically focused on low adhesion due to leaves, which I'm sure everybody has heard is quite a big problem for the UK. And it certainly is a problem in other parts of the world as well. So I'll go over some models that we've built and then look at a technique which we're pioneering at the moment to clean rail heads to give more controlled levels of friction. So I don't know how many of you are familiar with the University of Sheffield. Sheffield's located pretty much in the middle of the United Kingdom, perhaps towards the north end of England. The university's been around since 1905, but my department, which is mechanical engineering, is just over 100 years old. In fact, when in the year of its 100th birthday, I was celebrating my quarter of a century in the department since starting there as a student in 1992. So I haven't left since then. So that must mean it's a good place to be. You can see here the picture in the bottom left-hand corner is the very beautiful building that we're normally located in. Obviously, at the moment, we're locked out of that. We are starting to get a few of our labs open now, though, to get some of our research going. The picture in the middle is a building opposite the very old building, which is brand new. It's a £90 million teaching building that we've had commissioned with some very nice laboratories in it for undergraduate students. So the work we do in railway engineering, certainly within mechanical engineering, falls into 4 different areas, three of which I will cover today. So we have stress and wear monitoring. So this is monitoring of the wheel-rail interface. We're also extending that work at the moment to measure stress in rail, to look at buckling issues. We look at infrastructure, so overhead line, rail joints, and we're developing a brand new grinding technique at the moment. I won't be talking about it today, but at the moment we've managed to achieve speeds 3 times faster than the conventional grinding techniques that are used at the moment. So that's quite an exciting development. Perhaps the biggest area of my work is centered around friction management. So this is, first of all, understanding friction mechanisms in the wheel-rail interface, and how they change when you have third body layers present, whether they be natural third bodies like water or leaves, or whether it's mechanisms resulting from the application of, for example, top of rail friction modifiers or curb lubricants. And then finally, where I started in my work in railways, in wear testing and modelling of wear in railway wheels. So the focus of my work was largely around understanding the material removal mechanisms, but also to develop wear models that could be integrated into tools based around multi-body dynamic simulations to predict profile evolution. So breaking that down a bit further, you can see here a list of some of the projects we've been working on. So as I said, wear testing and modeling and understanding mechanisms. Wear transitions has been a big part of that. So how wear mechanisms change as the energy or T gamma level in contact increases. We have a huge database of wear values, which is very useful, and we're very happy to make that available to other people where we can for standard materials. We've built up a huge database of wear rates using our twin disc testing machine and our full scale rig. I'll be talking about the laser cladding later, so I won't go into that now, but another big area of my work is understanding the effects of third body layers. Like I said, whether they're natural ones or the result of applied products. Obviously that crosses over into friction management. We do a lot of work on applied products like traction gels and sanding to increase friction. They're obviously very widely used within the UK. And then top of rail friction modifiers, stick lubricants, and then understanding the causes of low adhesion or variance of friction in the wheel rail interface. So that's brought us more into the measurement of friction, and then developing solutions to provide more controlled levels of friction. This has been mainly focused on cleaning of rail and perhaps new technology that go onto trains, perhaps to replace sanding units that are used at the moment. Infrastructure, I won't be covering this today, but like I said, the most interesting work we're doing is around insulated block joints, which we use to create track circuits for signalling purposes. I do mention a little bit about that in the laser cladding case study. And also the high-speed grinding, the use of super abrasives in rail grinding to speed it up and to leave a better quality surface on the rail, both in terms of roughness and in terms of avoiding phase change and white etching layers. We've also had a big issue with Sheffield, where we have a tram system where bikes and trams have come together in perhaps a not so good way for cyclists. So we're looking at how we can perhaps help cyclists when they're riding on slippy rails. Finally, stress and wear monitoring. So we use ultrasound to look at interfaces, whether that be the wheel rail interface. We've also looked at the fit between an axle and the wheel, which will be very, very important for the integrity of the wheel set. We're also now looking at measuring stress within rails, which is quite a big issue worldwide as well. So we've got a project running with FRA at the moment on that, and with Network Rail in the UK. We work with people all over the world, and we're always looking for new collaborators. This is one of the benefits of working as an academic, is the capacity for us to network and make friends around the world who we can work with. there's a small collection of some of the people we work with. Hopefully soon we'll be able to go and start visiting them again when the current situation gets better. Okay, so that's a bit of background to the kind of work I do broadly. As I mentioned in the overview, now I'm going to talk through some case studies of some of the work we've been developing over a number of years, some of it. So I'm going to start with the ultrasonic techniques for characterizing wheel-rail contact conditions. And this certainly is some work we've been developing at Sheffield over probably a period of about 20 years. We have ultrasonic techniques now for looking at a wide range of interfaces, both dry, as the wheel rail interface will be most of the time, but also lubricated contacts in bearings and automotive engines where we can measure lubricant film thicknesses. We also have some devices in wind turbines as well for monitoring loading and stress levels and wear within bearings. So it's quite a diverse technique. Here we're using it very specifically for looking at the contact between wheel and the rail. It's very important, as most of you will know, to understand the conditions within the wheel rail interface. There's a contact stress that largely leads to the fatigue and wear mechanisms that occur within wheels and rails. So having a better understanding of the contact conditions can help us control those processes, hopefully reduce them, but also as well feed into better planning of maintenance schedules, so wheel turning or rail grinding. There aren't really any direct ways to measure the conditions. There are many ways to model them, and certainly having a better measurement approach will enable us to validate models better as well. So we've used three approaches involving ultrasound. So a lot of the work we've published has been around our ultrasonic scanning. So this is of static contacts. Obviously, that's useful in a sense. We can get very high resolution measurements, but wheels and rails are dynamic. You know, the wheel rolls down the rail. We need to understand the dynamic contact. So we moved on to use ultrasonic arrays, initially embedded in rail and then mounted on the underside of the railhead to give us the potential to take real-time measurements of the contact conditions. A quick explanation of ultrasound. So it's sound above frequencies of 20 kilohertz. A number of different waveforms can be generated. Largely here we've used longitudinal waves generated through the use of different types of transducers. You can see one here, a focusing transducer, which emits longitudinal waves of ultrasound to the surface through a water couplant, and it's focused through refraction down onto the interface between the two components of interest, and we can achieve a spot size of about 1/4 millimeter. This can vary as you use different frequency transducers. So what the choice of transducer will be dictated by whatever application you're looking at. We have quite a big contact to aim at in terms of the wheel rail interface. So we don't need really high resolution. So when you consider a real engineering surface, it has roughness, it has asperities, and that means when you load it against another surface, you get little pockets of trapped air. When ultrasound is incident upon an interface, where you've got metal-to-metal contact through the asperities, the ultrasound will transmit, but where you have air pockets, it will be reflected. So ultrasound reflects from an air interface. You also lose some of your ultrasonic signal through attenuation in the material. So as the incident waves passes down and then back through the top specimen here, some of the signal will be lost through attenuation. So in order to try and characterize the pressure within the interface, we have to use what we call a reflection coefficient, which we can get from our ultrasonic measurements. And this can be related to the contact pressure. The way we do that is through a spring model for interfacial stiffness. So you can see the equation there. Involves the speed of sound in the material and the frequency of the the transducer, and you can see the reflection coefficient R there. So that's the bit we measure from our ultrasonic measurements, and then that allows us to calculate the stiffness. And it's been found that the interfacial stiffness is proportional to the nominal contact pressure, certainly over the range of contact pressures that we're interested in. So when we're taking a measurement, when we're doing a scan, we will scan over the contact, but we also need to scan away from the contact to get a reference value for calculating our reflection coefficient. And this obviously takes into account the loss of ultrasonic signal through attenuation as it passes through just that top specimen as illustrated here. And so all the ultrasound will be reflected because it's at an air interface. So when we've done our measurement and gained our reflected voltages from our interface, we can obviously calculate our reflection coefficients. Then we can convert that reflection coefficient to an interfacial stiffness using the equation I showed earlier. And then we can convert our stiffness to contact pressure using a calibration. There are some more mathematical ways to do this emerging that would allow us to perhaps avoid a calibration. Calibration is quite a sensitive stage of the process because the calibration is very much affected by the roughness of the surfaces, as you might imagine. The transmission of ultrasound is very strongly affected by roughness. So when we do the calibration, we have to use surfaces similar to those to the actual specimens. So normally we use a separate loading device where we have a known contact area, and then we will do some point measurements as we increase the load in the system, increasing the contact pressure. Then we can define the interfacial stiffness from the reflection coefficient, and we get our calibration curve. We've got a whole series of these calibration curves built now for rail and wheels in different conditions, so run in, but also in a newly ground or turn state. So the very early work we did involved pressing together some specimens we'd cut from wheel and rail, just to show that the technique would work, I guess, and get some understanding of the output. And in itself, it's quite useful for validating certain aspects of contact models that exist. So we would do an area scan to capture the whole contact. As I said earlier, the spot size is about 1/4 millimeter, so that's our resolution. And we've taken the loads up to realistic wheel-rail contact loads, as you can see there. And this is very typical of the output that we get. This is quite a rough surface contact, as you can see. It's not particularly well run in this wheel and rail specimen, so there are some quite high pressure peaks. We've compared to Hertz contact analysis. We get quite good size comparisons. There are many reasons why maybe we shouldn't, obviously because we've got rough surfaces here. And our peak contact pressures are much higher than Hertz predictions because of that roughness. So there's a good example of the static measurements that we've taken. From that, we moved on to use some slightly different types of transducer. So first of all, we used an array. So an ultrasonic array is the kind of device that might be used in medical imaging, for example, so for looking in the womb of a pregnant lady, for example. So these have many applications. It's basically a block of, this array is a block of 16 transducers that can obviously take measurements across the width of the rail. So we tested this in our full-scale rig that you can see here. You see it uses an actual wheel, and underneath we have a rail which is pulled by an actuator. So we have a big actuator for applying the normal load, another actuator to pull the rail, and actually we have a further actuator that pulls the wheel, which allows us to impart some slip within the contact. So we've mounted our array under the point where the wheel contacts the rail. So the wheel doesn't move here, it's the rail. So we'll pass under the wheel with our array, and as we do that, we can capture information that will allow us to build up a map of the contact. And here are some typical scans that we've achieved. You'll note here we have multiple contacts. This was because our wheel was quite badly worn when we did these measurements. We have done some comparison with finite element modelling and rough surface contact modelling, and they're in reasonable agreement. So we're very confident in this approach moving forward. The only problem here is that we can only achieve very slow speeds in our rig, which is something we felt we needed to work on. So how could we build this technology in a way that would allow us to take it into the field? Obviously, people aren't going to be happy that we cut holes in bits of rail in the field and create some health and safety issues. So we needed to find a slightly different approach to capture interface conditions on the actual rail without cutting it in any way. So we moved on to use some flexible arrays. You can see here that they're mounted under the rail head, and now we're using what we'd call a pitch catch arrangement. So one array is emitting the incident ultrasound. It's reflected off the top surface of the rail where it will capture the interface conditions before being received by the second array on the other side of the railhead. So this is very different to the approach you saw before, where one transducer is doing the emitting and receiving. But this gives us the scope to go out into the field eventually, and that will be the next step for this work. But initially, we've trialled it on our full-scale rig again. You can see the setup here. The arrays are in a very similar position. And here are the scans that we got from, again, some realistic loads for wheel-rail interface. Again, a double contact. You can see now that we're getting lower resolution measurements. That's because of the setup we have to use in terms of the pitch catch. So that's the downside. But the upside is that this can be taken out into the field now, and in theory would be able to capture contacts at realistic train speeds. Obviously, there's a certain limitation here. We'll be measuring on one point on the track. So as some future work, we'll be looking to see how we could possibly build ultrasonic arrays into a wheel somehow to capture more information, obviously, as the wheel's going down the track. In terms of other work we're moving forward with in using ultrasonic techniques, as I mentioned, we're building devices now to try and measure stress in rail, again for field application, but there's also the possibility that we take measurements during rail production, for example, to understand residual stresses in rail, which is possible with the ultrasonic technique as well. So there's a lot more work to do here, and we'll be continuing with that as we move into the future. All right, so I'm going to move on to my second case study now. This is in relation to reducing wear in rail, and obviously possibly wheel as well, as either could be clad. So we've been for 5 or 6 years now working on laser cladding of rail. So for those of you who don't know what laser cladding is, it is an additive manufacturing technique. You can see the image here of the laser that might be used. Here it's cladding a cylinder. So the laser is fired at the surface of the material, and in the laser cladding technique that we use, the powder of a premium material that we want to put onto the surface of our component is fed towards the surface around the laser. So as the laser is heating the surface, it's melting the substrate, but also the powder as it forms a clad layer, which if you have the cladding parameters set up well, that will give you a really strong bond. A lot of the research we've done with the cladding provider has been in actually defining the best cladding parameters. So what's the best laser power, what's the best speed to move the laser at, what's the best feed rate for the powder, and optimizing those to give us a really good strong bond, and and to ensure that there's no embrittlement in the heat affected zone below the clad layer. It's very easy to clad things using this kind of technique. It's much harder to clad things and have a really strong bond. When we started this work, we found there wasn't very much work going on in terms of cladding materials to be loaded in a kind of tribological contact. Most cladding that was being done in the UK was really for corrosion protection. So for the oil and gas industry, for example, and maybe the nuclear industry, energy and power production. So we had to do a lot of work to understand what the best materials were to use to give wear and RCF protection. And that was what we did in a lot of the early work. So we were cladding using a wide range of materials. Some of those you can see here in the bottom right graph. So we were cladding cylinders and making specimens to use in our twin disc machine. So that within the twin disc machine, we have a wheel made of disc made of wheel material, which we load and roll against a rail material. In this case, the rail material was clad. We looked at different materials, different thicknesses, different layers of cladding. Some materials it's very easy to put second layers of clad on. Others it's not so easy. It depends on the residual stress state within the material, which does vary between different materials. We've looked at good clad. We've also looked at bad clad. This is to try and de-risk the process, to understand what might happen if worst case some bad clad got put out into the field. Our initial findings with the bad clad are that there is no catastrophic failure, which is a good thing. We've also looked at cladding lower grade rail material. So obviously you're putting a premium material onto a standard material to try and reduce the costs that may be involved in having a rail made entirely of premium material, just as an example. But actually the opportunity is there to actually go to a lower grade of rail. So in this case, we tested R200 with a clad layer of martensitic stainless steel, and this gave very good results. So much lower wear rates than, say, for example, R260 on its own. You can see here on the bottom graph, the best performing material we applied was a martensitic stainless steel by some margin. This is at 1% slip. We found going to higher percentage slip values that the clad material has maintained this really high performance and outperforms some of the premium grade rails that we've tested as well. So as you can see in the top graph, the materials A, B, C, and D are a series of premium rail grades that we've tested, but the clad materials are performing better. Obviously, the opportunity we've been looking at here is to clad new components, and we've mainly focused on high-value track components. We're not thinking that this is necessarily an approach that could be used for cladding long stretches of track, although that may be possible. The other opportunity is in repair of rails. So we're testing some repaired discs at the moment where we're cladding like on like. So we're actually cladding 260 grade powder onto discs to simulate a rail repair. Obviously, you get slightly different properties within the repair because of the thermal processing that's going on. And obviously, you'll also create a heat affected zone, which will come up to the surface. So we need to see what the impact of that will be. Just some examples of the surfaces post-testing. We've done wear testing and the clad layers see wearing a lot less than our standard grade reference in 260 grade. And this is reflected in the surface of the discs as well. In the rolling contact fatigue tests, we basically run out the clad layers. We've not achieved any cracking largely. You can see the 260 grade sample here in our test where we run some dry cycles, maybe 500, and then we start applying water to try and accelerate the crack growth. So after about 30,000 cycles, we're getting significant cracking within the 260 grade rail. Within the clad layers, we're struggling to find even any evidence that there's been deformation in the surface by that point, let alone crack roads. So this is looking very promising. We've done some analysis, obviously, of the clad layers post-testing, looking particularly at the heat-affected zone to look at the properties and how these compare with the bulk, examining the dilution zone at the point where the clad material sort of moves into being the bulk material. And everything we've seen suggests that as long as you're getting the cladding parameters right, that this will be good. An example of some of the RCF tests, you can see here the 260 grade reference material. Then we've got our 260 clad layer, and then all the other clad materials are pretty much running out before there's any sign of anything happening. May have been in one case some slight cracking in one of the materials, but the others are running out. So we're detecting cracks with our eddy current crack detector, and then afterwards we section to see whether there's any evidence of cracking if the eddy current crack detector is triggered, which it wasn't in the case of the clad layers. So small scale tests look promising. I should say it's much easier to clad a cylinder or a disc than it is to clad rail. Obviously cylinders are much easier to set up to clad than the relatively complex geometry of a rail or a wheel. So we put a lot of work into working out how we could clad rail. And you can see here we've used our full scale rig again. Here we've got a clad rail under test. At this point we weren't able to actually measure the profile change, so we're looking more at the size of the wear scar. This, in terms of indicating wear, showed that we were getting the same increase in performance as we'd seen in our twin disc tests. And of course, this was our opportunity to show that the clad layer stayed intact under the quite severe loadings where we were applying in our wheel rail interface. We also did a series of bend tests as well to look at whether we could cause any delamination in the layers, and we were unable to do that. And where we took specimens up to the point that they fractured, that they broke a long time after the standard grade rail. Again, some really good evidence of good performance. One high value track component we have problems with in the UK is an insulated block joint. So these are intended to electrically isolate blocks of track. And what we find when we have standard grade rail is that because of the stress is put into the rail by the passage of wheels, we get a flow of material over the nylon end post, which is positioned between the two bits of rail. You can see here that we managed to simulate that in our full scale rig. We pretty much bridged the gap with our 260 grade rail. We've used some quite severe test conditions here. We wouldn't normally expect to see 3% slip on the top of the rail. We were trying to accelerate the test. But if you look at for example, the clad layers at a much higher percentage slip level are outperforming the 260 at a much higher slip level, and 260 at 3%, the gap was closed very quickly. It seems like quite a simple failure in some ways, and in fact the way to solve it or to remove the material is simply to come along with a Dremel tool and cut the material that's flowed away. However, if the track circuit fails, then the line is shut, and this can lead to enormous cost in terms of delay minutes. So the industry is very keen to look for a solution that doesn't involve the material flowing, and cladding could certainly be that. We've sectioned the rails after to have a look at how they flowed. You can see the 260 grade examples here, and the very large flow apparent on the standard grade material, particularly at high slip. When we look at the clad material, there's a little bit of lipping, but that's as far as it goes. The material does not flow any further. And even here on the 260 grade material, where we have the big deformation at 3%, that's kind of more bulk deformation. There is a lot more material flow of very thin layers that bridges the gap. Now these tend to form and then break away and then reform, because obviously they're quite weak and easily fatigue and break. And we also closely examine the point where we run the clad 2 along the rail to look at where the heat affected zone is coming up to the surface. As you can see here, this is post-test. There's no evidence of any problems within that region, which could potentially be a point of weakness. The next step in this work is to carry out some field tests, which we'll do at the British Steel plant at Scunthorpe. So we've had a series of OBJs made up, and we'll be testing them there as soon as we can at the moment. British Steel plant is still running, but we're unable to go there at the moment because of the COVID crisis. One thing that cladding the rail obviously means is you have very hard rail, and people are always very keen to understand how this will impact on wheels. So we will probably be made of a softer material. There's a big concern that hard rail means lots of wheel wear. So we've put a lot of focus onto understanding what the effects of having harder rails may be. There is a reasonable amount of work in the literature in this area. However, it's quite fragmented. There's very little work done at the same contact conditions, for example. So it's quite hard to compare relationships. And there isn't a big breadth in contact conditions. So you can't look at what happens as you move through wear transitions and you get up to really severe wear. Quite a while ago, somebody put some relationships together to show how wear varies with the ratio of rail to wheel hardness. So as you go across, they were assuming that the rail hardness is increasing, but obviously on the left-hand side of the one there, the wheel is harder, and on the right-hand side it's softer. They were showing through this that certainly when you have a harder rail, wheel wear is independent of rail hardness, which is very interesting and quite reassuring for the people that own and maintain the wheels. So we decided to do some more work looking at different contact conditions. We had a range of rail hardnesses provided by the different cladding materials that were trialled, and we also looked at some premium materials as well of different hardnesses. So this was all done through twin disc testing. We found with the clad materials that we saw something that reflected what was shown in that schematic, that as you increase the hardness of the rail, and note this is post-test hardness, so this is after work hardening of the rail material. So rail wear reduced largely as the hardness increased, but wheel wear remained relatively independent of the rail hardness. So what was causing this? Well, when we sectioned the wheel discs and looked at the hardness going into the material, we found largely that the hardness of the wheel material was staying constant, so you can see here. So regardless of the rail material, it was running against, it work hardened to the same level. So that was showing us that the wear of the wheel material for these test conditions, which was 1% slip and about 1500 megapascals, yeah, the wheel wear was not affected by the rail that it was running against. We did some measurements of the roughness as well and the change during the test, which gave us some interesting data. And it showed there was a threshold at which point the change in roughness dropped from being quite high to being below 0, which is showing us the really hard materials we were testing were I guess being polished up or abraded. So they were wearing in a very different way to the kind of ratcheting mechanism you might see in the softer materials. The change in wheel roughness reflected the change in the rail roughness, so whatever the rail changed to, the wheel kind of followed, and being softer, that was kind of understandable. We've now tested at some slightly more severe test conditions, so we jumped up, for example, to 10% and 20% slip. These don't occur very often, fortunately, but we saw some interesting changes in the wear relationships. So, for example, at 10% slip, we weren't seeing a big change in the rail wear rate as we increased hardness, and the wheel wear relationships were becoming a little harder to define. Obviously, as you increase the slip, you bring in more temperature effects, and of course, the softer wheel material will be less resistant to those higher temperatures. This was very evident in the 20% slip tests, where we were seeing actually not a big change in the rail wear, because premium materials and in particular the clad material very resistant to temperature change and not being affected too much. I think there's a need here for us to look more closely at how the hardness is changing when the materials are reaching the high temperatures apparent in the contact. So actually during the test, the hardness may be varying from what we're measuring afterwards. So perhaps an interesting area to do some more investigation in there. Largely though, I think we can say that using harder rail or using clad layers is not going to be too detrimental to the wheels under normal operating conditions, which is good. So my next case study is on modelling friction. While I'm showing here an example where we've done some work on looking at the effects on low adhesion due to leaves, obviously those of you that don't suffer from this problem, very lucky. It's a big problem in the UK, but this same approach can be used for building models to look at other things that get into the interface. And in fact, we've just finished a project with FRA where we built a similar model to look at top of rail friction modifier performance, both in terms of its friction effects, but also in terms of consumption from wayside applicators. So the idea behind this work is that we do some tests on either a small scale or a full scale rig to produce some creep curves, and then we use those to parameterize a model. Here we followed the kind of POLAC modeling approach, as you'll see when I go through. So low adhesion is a constant problem in the UK. The biggest problem, I guess, during autumn is leaves, but we also have a phenomenon which is known as wet rail. So it's when we have oxide and small amounts of water in the contact, causing low friction. Any more than low amounts, so for example, if it's raining, leads to the rail surface being cleaned. So actually a lot of water is okay, a small amount is a problem. So at dew point in the morning, for example, whereas a rail surface is drying after rains occurred, then low adhesion incidents can occur. In autumn, the causes of incidents like signals passed at danger or station overruns it splits about 50-50 between leaves and wet rail. But obviously, wet rail can occur all year round, so it's actually a bigger problem. It just gets a little less media exposure. A lot of small-scale testing has been carried out to examine friction levels, but very little full-scale. And in fact, while it's been a problem for a long time, detail of the mechanisms is only really emerging now. So, for example, we've done some work recently which we published on the role of tannins in leaves, which hadn't been explored before. So with the tannins present, you get very low friction. If you can suppress or remove the tannins, then the friction rises quite significantly. Models for real rail friction obviously exist, and some have done for a long time, like POLAC, ECF, contact, and so on. But none really deal with the low adhesion contamination conditions. It's very important to be able to predict these so that you can simulate how trains will behave when there's low friction. So that can help in mitigating the problem or in developing better braking strategies. So the aim of this project was to do just that, to build a model to predict the impact of leaves. We carried out the full-scale tests on the University of Huddersfield's full-scale bogey test rig. The aim now is to integrate the model we built into either multi-body dynamic simulations to look at full train behaviour or into a train braking model that exists, Labrador model. So you can see here a picture of the rig. It's quite hard to fathom what's going on here. So the yellow structure above the bogie, which you can just see there, is obviously all the loading apparatus. The rail loop is actually below floor level in that picture. We were using a Y25 freight bogie. It's tread braked, so in order to generate leaf layers and then not remove them, we only braked on one side. So we jacked up the bogie on one side, we braked on that side, and that meant we could generate and run leaf layers on the other side. So our standard approach was to run, once we've generated the leaf layer at low speed, we'd run the rig up to rolling speed, and then we'd apply a brake force until there was wheel slide, and there was a rudimentary wheel slide protection device built in to protect the system, or until the maximum brake force was applied. And once that was reached, then the roller was decelerated to 0 velocity. And in that braking event, we were able to capture data that could give us a creep curve. So you can see here how we were building the leaf layer. So we either fed in a tape of leaves, or we were feeding in leaf material through a chute. And you can see how the leaf film was after it was initially created on the left hand of those three images, sort of brown crusty layer. As we carried out braking events, then the layer blackened, and this is what people typically think of when we talk about leaf film, is this black layer. After about 5 or 6 braking events, the leaf layer was removed. We slightly wetted the leaf layer before the brake test. Moisture is very important in this process. A dry leaf layer will probably not be a particular problem. A little bit of moisture, though, will make it incredibly slippy. There is a video here. I won't show this in the interest of time, but it showed the rig operating and us feeding those taped together leaves in. A rather laborious process creating the leaf layers. Happens much more easily in the field. What's more interesting is some of the data. So initially, we did some dry tests to try and benchmark the performance of the rig. It hadn't been used for friction measurements before this project. So you can see here we've got friction coefficients against traction coefficients against slip. So the one being 100% slip. You can see here that we're getting very typical dry creep curve shapes, or a peak and then dropping off as thermal effects kick in. We've tested a range of loads and speeds, and we've compared with some locomotive data that's been published, and we're getting very similar shaped curves. Getting slightly higher friction in the Harold rig. This is typical of lab testing in dry conditions. Obviously, you do really have dry conditions in a lab. Outside, there will always be some level of moisture present, but also in a continuously rotating rig, you generate thicker oxide layers, which then lead to higher friction levels. So that was good, that looked promising. Then we built the leaf layers and we started to test. We tested again over a wide range of loads and speeds, and pretty much whatever we did, we got really, really low friction. So we're getting below 0.02 in a lot of cases. So if you think about a really high quality formulated engine oil that you put into your car, typically they would give friction levels of around 0.05. So leaves are a way better lubricant than a formulated engine oil. We found even as the layer was degrading and being worn away over repeat tests, the friction levels stayed very low. So we got an interesting new testing technique now that can, at least on its own, be used for testing mitigation products, which is good. So we have all the data. How do we turn it into a model? Well, this is where we started our parameterization process. I'm not going to go too much into the detail here. If people are interested, they can certainly follow up with me. This is the dry data, but obviously we did it for the leaf data as well. What this allowed us to do was to build a tool, and you can see the graphical user interface here, that allows us now to set wheel-rail interface conditions and vehicle speeds and creepage conditions, and we can now select contaminant types. We've looked at other contaminants as well, look at the amount of contaminant, and the outputs of the model is creep curves, as you can see here. So if you selected your conditions for contamination or no contamination, it will generate a creep curve. You can then feed into a multi-body dynamic simulation or a brake model. So this model is available if anybody would like it. It's freely available. If they contact me, we can provide it and the code as well. Finally, though, how do we deal with the leaf problem? The industry for many years in the UK has used water jetting as a leaf layer removal method. This involves use of a very bulky train with 2 locomotives and a lot of water wagons. There's a lot of pressure now to reduce water usage, so the rail industry are looking for alternative systems, and we've started developing one that's based around the use of dry ice pellets. So essentially we're firing dry ice at the rail head through a nozzle which emits it in a stream of supersonic air, so it's going very fast at the surface. It's very cold. It freezes the contaminant, which is then brittle. The kinetic energy of following pellets helps to remove that, but also the pellets sublime on the surface, so they turn back to gas, and in doing that you get an 800% increase in volume in a very short space of time. So you can see images of the pellets here. A whole variety of different sizes can be used depending on the application. We get asked a lot, is the temperature a problem here? Well, the bulk temperature of the rail in the time the rail is exposed to the dry ice is not going to change. It's about 0.005 of a second that the dry ice is hitting the rail. So you can see on the graph there, you'd have to have exposure for minutes to get a bulk temperature change. So it has no impact on the bulk rail cracks, IBJM posts. It also doesn't influence the ballast, which means it can be used over switches and crossings. So the water jets that are used are so powerful that they will displace the ballast if they're not directly firing on the rail, which is a big problem. I'm going to show you a quick video of it in operation. This is in the yard of the tram network in Sheffield, Supertram. Hopefully you can see this okay. So we've got it mounted on a road-to-rail vehicle here. You can see the jets now firing here. We've simply got wet rail, so it's oxidized, but we're completely removing the oxide and the water as well, and leaving a nice clean railhead. We've done swabbing post-test, which I'll explain in a few slides time. So there we're going over S&C. You can see the water being removed and all the debris track going. We have tested on leaf layers as well. Because of the success of the trial with Supertram, Network Rail gave us 5 sites to clean over last autumn across the UK. The one I'm going to focus on was the one where we tested in Scotland, near Oban, very beautiful place, Oban. Not so much in autumn or winter though, when it's very cold and wet. So we were cleaning 6 miles of track each night, essentially. You can see the setup here. We've got a Land Rover road-to-rail vehicle, and our equipment's on a trailer this time. But you can see the before and after images here of the clean. Very effective. We took swabs to indicate how much material was on the track before cleaning. So here, the left-hand swab, heavily coated in oxide. Here, less material. The only material actually that is on the swab is that came from the edges of the clean track. So in the middle, number 2, we're not cleaning anything off. We analysed that. That essentially showed that on the swab after cleaning, the only materials that were present in our analysis were the swab materials. So, very successful trial. We did do some tests as well to try and show what impact the clean rail had on train braking performance. You can see here a Class 117 DMU. This is a very antiquated train. It counts as a heritage vehicle, so it wasn't the most modern technology, but it was all we had available to do the testing on. They didn't mind too much if they got wheel flats in the tests, so that was good. Because on the leaf layers, the wheels do slide completely. So you can see here the braking performance with a leaf layer, and after we've cleaned the rail, the braking performance is returning to dry levels. So very promising. That has led to a series of new trials happening, well, this autumn, in fact. So we're working with another light rail system, the metro system around Newcastle, who have their own railhead treatment train, which we can mount our equipment on. This will allow us to use technology in an operational setting, as they do cleaning loops twice a day during autumn, and obviously test at higher speed. We've only gone at 10 miles an hour so far on the road-to-rail vehicle variant. We will be doing a season-long trial now, though, with Network Rail during autumn on the whole of the West Highland line. So again, the track near Oban, but going a lot further to show the reliability over a longer-term trial. And we're also going to be fitting the cleaning equipment onto a passenger train. Obviously, the thinking is that if a passenger train is able to clean the rail during the day in more regular intervals, get more cleaning during the day, then the rail is going to stay clean. If it's done overnight in track possession through a road-to-rail vehicle, a railhead treatment train, it's only going to get cleaned once a week. Perhaps in a peak of autumn low adhesion, maybe twice a day. So some really exciting projects going on. I think for us as academics, it's great that we can see our research turning into some technology that's making some impact with the railway industry, and hopefully the case studies I've shown illustrating how we take our research out of the lab and start to make a difference for the industry, either through measurement tools or where reduction approaches and low adhesion modeling tools to help train designers and brake system designers, and then practical tools to try and maintain the rail in a better way. So that's everything I had to say. Hopefully that's been an interesting snapshot of the work that we're doing for you. As I said, covering the route we take to go from fundamental understanding to developing tools that can be implemented in industry. If anybody would like more information on any of the work I presented, or any of the other projects which I listed at the beginning that I haven't been able to squeeze in, then please do send me an email. There's my email address there, but you can find me easily on the internet as well. So thank you very much for the opportunity to present.